Hello, everyone. People who are online as well as in, in the seminar room. And thanks to Chris for organizing the seminar room. And it's our great pleasure to have Professor Mahendra Kumar Verma from IIT Kanpur. So Mahendra is an expert in turbulence, magnetohydrodynamics, thermal convection, stably-stratified flow. He did his PhD at University of Maryland in 1994. And in the same year, he joined IIT Kanpur as a lecturer. And presently, Mahendra is a chair professor at IIT Kanpur. And he's also a fellow of Indian National Science Academy and fellow of Indian Academy of Sciences. And he won several awards, including Swan Jayanti Fellowship. And Mahendra was my PhD supervisor as well. And today he's going to talk about, is there a universal theory of turbulence? Over to you, Mahendra.
Okay. Thanks, Abhishek, and thanks to the Coventry friends for the invitation. It's a difficult time, and so it's good to meet at least virtually. I hope things are fine with everyone in Coventry. Okay, so this is the title of the talk. Is there a universal theory of turbulence? Okay, I will explain a bit more as we go along. And this work is a joint work of many PhD students, like Abhishek being one of them. Shashwat and Manohar were later, and there were quite a few other work, but I just named just some of them. Okay, so universal theories. No, I mean physicists like universal theories because it helps to solve problems of different sorts in one framework. Like Newton's law of motion is three laws which can explain all sorts of motion, from astrophysical to at a molecular scale. Law of gravitation, law of phase transition, quantum world, we are Schrodinger equation. Now, similarly, I mean, there's a search for one theory of turbulence. Okay, and we don't have one, but people think that if they solve one particular problem, that will be called universal theory. But my answer is no. I mean, that's why I can tell you from the beginning itself. I can't say my answer. My take is no. I mean, my vote is for no. So I will tell you why. So just to advertise, I wrote several books. So the present talk is basically here in energy transfer in fluid flows. This is something which I wrote a bit before on buoyant flows, and today's talk is essentially in this paper, variable energy flux. And there's another work which we did some time back with Abhishek being one of the authors. So this is for thermal convection and stably stratified flows, and all this will appear today in the talk. Okay, so let's start with the simplest of all. I mean, Navier-Stokes equation. Incompressible. I will just stick to incompressible flows in today's talk. And everybody is expert, so I don't need to explain this stuff. But yeah, so we just focus on incompressible flows. And I'm going to, okay, so let's see. So turbulent limit is when Reynolds number is large, right? I mean, this is the limit when Reynolds when we have turbulence, R is large. And so there's a millennium problem. Okay, now millennium problem, let me just show you the statement. So prove or give a counter example of the following. In a three-dimensional space, in 3D space and time, given initial condition, there exists a vector velocity and a scalar pressure field, which are both smooth and globally defined, that solve the Navier-Stokes equation. Okay, so it's not even clear that there exists a smooth solution. Okay, there exists smooth. This is not right now. Nobody has proven it that there is a solution. So this is the thing. You prove it, there exists a solution, or give a counter example, show that it doesn't exist. Okay, so there are people who are looking for weak solution, strong solution, and I normally say that these are mathematicians. Okay, there are of course some physicists are doing it, but this is basically, for me, I'm not interested in this problem, and I'm not interested in this $1 million prize. Okay, so in physics, in fact, there are of course a lot of work. Some of it comes from UK, but the theory which is often quoted is Kolmogorov's theory in 1941, and it deals with homogeneous and isotropic turbulence. Okay, it's basically in a turbulent flow. Look at flow which is somewhat in the away from the wall, so it is homogeneous and isotropic. And for that flow, I mean, this is one of the simulations done some time back. So here you can see that vorticity. There's no, I mean, it's a periodic box, so flow is every point is equivalent to any other point statistically. Okay. Now for this flow, Kolmogorov gave a theory, but I just said this Kolmogorov is one name. G.I. Taylor, Batchelor. There are lots of, even before that, lots of work has been done now. Okay, so I'm not going in historical perspective, but I'll just put one name. In fact, it's called Haworth-Kármán equation. Okay, so this starting point I'm going to show sometime later. So take 2 points. And we look at the velocity field at these 2 points, ux and ux plus r, and we call it also u prime. Okay, so just for shorter notation, u and u prime. Okay, the u and u prime, and they're separated by distance r. And everybody knows this, but I'm just motivating the today's talk. So what Kolmogorov showed, that when viscosity goes to 0, and for homogeneous and isotropic flows, and if it is forced at large scale, okay, force at large scales. If you do that, then this quantity, the third order structure function, okay, so the velocity field here and velocity field here, component along r, a cube. So this minus 4 by 5 pi is a cascade rate with energy flowing from large scale to small scale. It can also be rewritten in this form.
Priorities to get other people away from the back.
Is there a, so u prime minus u whole squared. So this is also another way to write it. In fact, I'm going to motivate this one rather than that in my coming slides. Okay, so this is Kolmogorov's statement, and he was a mathematician, and he kind of wrote this. And of course, the phases we interpret in as a Kolmogorov 5/3 law and so on. But this is what K41 is. Okay, now let's look at a little bit on K41. That will tell us the limitations of K41. Okay, and that will tell us that well, the world is more complex than what K41 describes. Okay, so K41, no need to get into these steps, but this is correlation. Right? So there's 2 points, u and u prime. So you take a correlation. It is not this kinetic energy. It's a u and u prime, 2 different points, and that correlation is equal. I mean, if I look at the d by dt, a time derivative, it is one term is this term, which we just saw, divergence of this. Okay, but here the 2 points are separated by L. I'm changing my notation. Okay, so I wrote R there, but the difference between the distance between 2 points is L vector. So this L is scalar. It's isotropic, so you make scalar. So divergence with related to L. Okay, now it's isotropic, so it doesn't depend on theta, and so theta and zeta doesn't depend on. And this is coming from force correlation, and this is viscous term, u and u prime. Okay, so these are 3 terms which this is Kármán-Haworth equation. Okay, in fact, Kolmogorov took it and he went a step further. So here, this written as TUL. Okay, it's an energy transfer in some sense. Okay, but he didn't write well. This is called TUL, and this is a force correlation. Force is at large scales. Here, this LS is for large scale and dissipation. And look, if force is at large scale, then we can easily argue. I'm not going to discuss it here. This is the cascade rate, energy cascade rate, which goes from large scale to small scale. Okay, because force applied at large scale must be equal to energy cascade rate, and this must be equal to minus TUL. Okay. Now, if minus TUL is a divergence. You know, the divergence L. This quantity is called S3L. It is not same as Kolmogorov's quantity, but okay, is another structure function epsilon L. Now, just simple divergence formula: 1 by L squared d by dl S3L L squared is minus epsilon. Okay. Now this will give us that 4/3 law, not 4/5 law, but 4/3 law. Okay. Now this is how one can derive this. I mean, this is not, I mean, sometimes we find the derivation to be too daunting, but I kind of dug into it in recent times, and I saw, okay, this is the gist of the proof. Now, what is the limitation of this proof? Now, this proof, we assume that forcing at large scale, okay, and that plays a major role. That is a constant here. If this is not constant, then this could be function of L, right? I mean, like in thermal convection, forcing is at all scales, right? I mean, the plumes, small plumes, large plumes, all of them are driving the flow. Or in a stably stratified flow or in MHD, magnetic field is acting at all scales. So then this quantity is not a constant anymore, and this formula won't work. In fact, of course, Kolmogorov said is no. I mean, this formula is only when large scale forcing is there. So you can immediately see that there are many practical problems which we use all the time. It's not going to work. And also, flow is homogeneous and isotropic for this derivation, and flow is not homogeneous and isotropic in general. Though, if you look at very small scale in hydrodynamic turbulence, well, not very small scale, but smaller than the large scale, away from the walls, in real flows, you find isotropy. It's true. I mean, it has been shown experimentally and simulations. Flow does tend to become isotropic in the intermediate range, but that is only for hydro when forcing at large scale. Okay. Now, if you force at all scales, then there's a violation of this law. Okay. So let's see. So where are the missing pieces in K41 theory? And I think we need to look at it. Forcing is only at large scale, but in real life, forcing is at everywhere. I mean, everywhere means all scales. So we are talking about multi-scale problems. So you're forcing at all scales, and also forcing is anisotropic. Like in magnetic field, which many of you work in your lab, like Alban is working on quasi-static MHD. All that, well, I mean, for a lot of times, that flow is anisotropic. And also, if you just stick to hydrodynamics, hydrodynamic turbulence, then higher order correlation. Okay. In fact, people have been really bothering about this part, okay, which is an important problem. So Kolmogorov theory talks about only S3, third order structure function, but what happens to SQ of L? Okay. Now that remains still a challenge. We still don't have a theory from first principle how to compute SQL, but my interest has been basically focused on these aspects, forcing which are different than, which is multi-scale forcing and anisotropy. Whether we can also construct, people have started having it, structure function, which is not only function of L, but also function of theta, which is, now we have this 2 vector L. Now, this L depends, I mean, we can just think of a Z axis, and it can depend on theta. So there's a mean magnetic field, and so correlation will depend on where you choose your L. Is related to the mean magnetic field. Okay, so anisotropic structure function will come here. Okay, now I hope I've given enough motivation that, okay, I mean, Newton's law is fine for law of motion, but turbulence is basically a microscopic phenomena, and no, we need to have, I mean, we are stuck with different systems having kind of different phenomenologies. Okay, but there is certain commonality. That's what I will try to motivate. There is, it's not that it's just too diverse and we can't say anything. There are certain common things one can say. Common framework, well, at least one common framework. I mean, there could be many, but one common framework I will try to motivate. Okay, now present focus among some phases, not all. Well, in fact, the number is dwindling a lot. This was one of the major focus, that you stick to homogeneous and isotropic for flows and look for qth order structure function. So Kolmogorov proved for 3, but you do it for any arbitrary q, and this is called basically this is multi-scaling of turbulence. Okay, but I will not discuss this. Zeta q, it remains a challenge. There are models, in fact, a very nice model, Lacey-Wake model, multifractal models, but there has been a lot of attention in the past. Then for whatever reasons, I mean, the funding is cutting short in those fields, I don't know. This effort is shrinking over time. Okay, that much I can say from my experience. Now, so some people claim that, okay, if you get zeta q, you solve the problem. But I mean, from what I believe, the world, I mean, the turbulent phenomena is so rich and it has different facets. So I will not say that if you solve zeta q, you solve turbulence problem. Now let's look at our perspective will be a bit different. We'll go in the spectral space and look at energy flux. That is what I've been doing it for now several decades. So I will just focus on energy flux and try to make some common framework. That's what I'm trying to motivate in today's talk. And please stop me if something is unclear or I make an error. Now we write the equation, Navier-Stokes equation, in Fourier space. Okay, so this is a nonlinear term. A nonlinear term becomes a convolution. So this UK is UP and UQ are Fourier modes. So it's easy to derive. I mean, I'm sure everybody knows this, but I just written this k dot UQ, and so it's a convolution. U dot radio becomes convolution. There's a pressure term, and I write the force in two different ways. So the large scale forcing, I keep it like LS, and this forcing is a forcing active at all scales. Right? FUK can be everywhere. Like buoyancy is everywhere, gravity is everywhere. Well, buoyancy and gravity are related, but stability-stratified flows have slightly different kind of forcing. And MHD, J cross B is here. Okay, so Ekman friction is here. So this force, I keep it, is body force, some people call it. Okay, so Kolmogorov focused on this force, but I'm interested in this one. Okay, and for today's talk, we'll assume that those forces are anisotropic, but we'll make some kind of average over theta so that we can talk about one quantity called flux. Okay, it could be, it is anisotropic, but I'll formally argue that we have cumulative quantity coming out of a variable. So I'm coming to that in a minute. Okay. Now, from this equation, if I just multiply by U star K, dot product this, and then you can get equation for the energy. Okay, so this energy is modal energy mod UK whole squared by 2. Okay, so this is a modal energy, and this equation, well, I mean, let's just keep this in mind. So this is the nonlinear term, and this is also called TK. Same thing, but as Kolmogorov, but it's TUK. Kolmogorov was saying TUL, but now we call it TUK. This is coming from the force term, and this coming from large scale force, and this is a viscous term coming from the viscous term. Okay, so well, this is just straightforward derivation. Okay, now it turns out this derivation is one-to-one mapped to a real space derivation of Kolmogorov. Okay, now let me show you how. So this is a connection. In fact, I think it's interesting. I didn't see this in most, I mean, literature. I have not seen this, but it's just straightforward. So I wanted to just write this. So in Kolmogorov derivation, you might have seen this stuff in the top, right? Well, hat is a Fourier transform. So Kolmogorov without hat, Kolmogorov has no areal space. So this is a correlation. This is the energy transfer term, divergence of u minus u prime cube in some sense. This is this forcing term and coming from viscous term. Okay. Now here this is connected to the Fourier space nonlinear term, Fourier space LS term, and Fourier space DUK. It's one-to-one, except you have to do a Fourier transform of Kolmogorov's or Karman-Haworth equation. Okay. Now, and I guess it is known. I mean, but anyway, this is just this important piece to see the connection. And of course, this gives us epsilon here, and for I mean, this will give us the flux, which I'm going to come in the next slide. Okay. Now we have did in the past, but I will not discuss too much of that one. So these three modes, energy, they have certain meaning. One is a giver, one is a receiver. So energy is flowing from this mode to that mode, and one is a mediator. Okay, but we will not discuss that. It's a very nice formalism, but we can skip that for today. Okay. Now, so let's look at this TUK, which is a mode, this energy transfers, among modes. Now, if I integrate over a sphere of radius k0, there's a radius k0 sphere, so k less than k0. So if I integrate this, sum integrate, and take a negative sign, that is energy coming out of the sphere through nonlinear term. Okay, so or it could be coming in. I mean, depends on the sign. If this term is positive, the whole thing is positive, the energy is going out, the nonlinear energy is going out, and this is a flux. Okay, so this flux is that this is a flux. Now, of course, there could be forcing at all scales, right? Like buoyancy, magnetic field. So here I have the wheels. The wheels are the forcing. Okay, I mean, it could be a magnetic forcing, all sorts of forcing, and this red wiggles are dissipation, like heat waves. So these are wiggles, and we'll assume right now that it is everywhere. Now, so this flux can change because of this blue wheels and red wiggles. It can change. Now, let's see what happens. Now, so if this forcing is at all scale, then this flux will not be constant anymore with wave numbers. So the flux will change with wave number. Like Kolmogorov theory, Kolmogorov flux is constant, but in our theory, this flux will change with wave number. Okay. Now, how does it change? It's quite easy to derive. In fact, this is what when Abhishek was there was in Kanpur, we have been playing around with this for a lot. So this flux is so we have two spheres. One is white sphere inside, and this one sphere, and with radius k. So this is white sphere is radius k, and the bigger sphere, which is yellowish sphere, is k plus dk. Okay. Now there is forcing. These guys are there. This blue wheels are there, and there's a dissipation as well. Well, Ekman forcing is everywhere, so that kind of forcing could be there everywhere. So this kind of forcing will change the flux. So this pi k plus dk and pi k need not be equal, and we can derive this. So pi k plus dk minus pi k is what is coming. I mean, so energy supply. So this is energetics. Totally, this in fact is exact equation. So energy coming, this energy coming because of external force or body force, Fk integral dk minus dissipation dk. These are vectors dk. But if now I want to make one more remark that this pi k is a scalar. It's not a vector. Okay, it is cumulative. Even though the forcing may be anisotropic, but we just sum it up. I mean, in fact, this was one problem which I had with the referee. So pi k is not a vector. Pi k is an integral. It's a tk. K less than k0. Okay, so it's a sum. So this tk can depend on theta. Okay, but when I sum it up, I get one number. Of course, we can construct a more refined thing like ring to ring transfer, which Bogdan, I don't know he's there in the audience or not, but he did that some time back. So there are ways to construct nonlinear energy transfer, but flux is a scalar. Okay. Now, so the difference is coming from essentially energetics, is coming from the force and dissipation. Okay, dissipation will decrease the flux as with wave number when you go out, and the flux, the forcing will increase it. Depends on the sign, of course. If Fk is positive, if I pump in energy, the flux will increase with K. If you dissipate over wave numbers, then flux will decrease with K. Okay, this is just straightforward logic we can apply. Now, if I take the derivative of this, then I get this equation. So rate of change of pi. Now, I also would like to say that these are fluctuating quantities, but we are doing some kind of ensemble average or temporal average. Okay, so we do this averaging. So it can change with K, with forcing, large scale forcing, and dissipation. Okay, so this is the key equation for me, and this we call it variable energy flux. Flux is changing with K, and we are focusing only on the velocity field. Okay, now we can also do it for magnetic field or for temperature field, but let's just for today's talk, we'll just focus on on this velocity field only. And so this force appearing in the velocity field, J cross B or buoyancy or Ekman friction and so on. Okay. Now, I hope this part is clear, and this is just straightforward. There's no complex logic involved, and this is exact as long as we do averaging. Okay. Okay, and this is exact. In fact, it is the same footing like what Kolmogorov had, like Harworth-Kauerman equation. It is it's one-to-one map. If I do the Fourier transform that, I'll get here. Now, inertia range behavior. Okay. Now, inertia range means I'll assume that viscous forcing is weak, and the large scale forcing, which typically is, well, when I'm small. So those two terms will be. So I just want to make that. So basically, we will ignore these two for most of the talk. This one, if I focus to inertia on the inertia range, and we just go to inertia range. So only one part. Okay, let's just simplify our problem. And if for this case, let's see what are the scenarios. There are 4 scenarios, and Kolmogorov theory is only one scenario. Okay, so what are the 4 scenarios? If this is 0, if the forcing is 0 in the inertia range, which is the case for Kolmogorov theory, because Kolmogorov theory assumes that forcing is only large scale. So there's no inertial forcing. If forcing is 0, then 2 scenarios. We have 0 forcing, so flux can be 0. This is 0 flux, or flux can be finite and constant. So this part is flux is constant. Okay, the two. And this is also a very important problem. It is called absolute equilibrium theory. Absolute equilibrium theory, which we will not discuss today. This is Euler turbulence. It's a flux is 0. It's equilibrium theory, and so there are 2 scenarios for the case when flux is forcing is 0 in the initial range. But there third scenario is when this injection is negative. Okay. Now this forcing is taking away energy from the kinetic energy. Okay. Now stably-stratified flows or Ekman friction or in fact quasi-static MHD turbulence, they pull the energy out from kinetic energy. You know, it goes to either direct dissipation or goes to magnetic field or potential energy. So in that case, what happens to the flux? So if this is negative, this one is negative, then the flux will decrease with K, right? So flux will, so this is the flux, y-axis is the flux will decrease with K. Okay. Okay, this is the third scenario. So this is quasi-static MHD. MHD also comes in that. This is what we have been thinking. And stably-stratified flows, SST. Now, what about this one? This is when this forcing is feeding energy, okay, to kinetic. Now, what can happen with kinetic energy feeding? Like in convection, the fluid is at rest and we start heating, then the flux will increase with K. Because this term d pi by dk is positive, so flux should increase with K. In shear, the flux should increase with K. Okay, so these are predictions. Flux, unfortunately, I didn't see a literature where flux has been computed, but you expect the flux to increase. Okay, so scenarios when we pumping energy, Rayleigh-Taylor flux should increase with K. Okay? So thermal convection comes in this class. So at least we know this convection comes in this class, and shear should come in this class. Now, so looks like, well, to me, I mean, we've been doing this for quite some time. It looks like is one framework to discuss various sorts of turbulent flows. And so, yeah, so this could be one way to say, well, there's no universal theory, but well, there's one common framework motivated by the flux, Kolmogorov flux ideas. Now, Kolmogorov theory is, as I said, it corresponds to when forcing is 0 in the initial range, and it is straightforward, flux is constant. And this is equivalent to that 4/3 law, okay, or 4/3 or 4/5 law. These are equivalent, and this is exact. Okay, this relation is exact. However, 5/3 theory is not exact. 5/3 theory is derived using dimensional analysis, and in fact, 5/3 we know that there is a correction to 5/3, so that is not exact. Okay, so this one is dimensional analysis, and there are corrections to 5/3. Okay, so we have to contrast what is exact and what is not exact. Okay, so let me just make a remark here. So pi q average. Okay, so I take a flux, which is fluctuating quantity with wave number. You know, even for hydro, at a given wave number k, the flux will be fluctuating. And is it equal to pi average to the power q? Are they equal? It turns out they're not equal, and that is a one component for intermittency. And so that's why 5/3 is not exactly correct because of this correction. Now, need to explore general turbulence beyond K41, and I motivated quite a few examples. I will just try to basically discuss a bit about these two. And MSD also, I think there are interesting conclusions can be drawn from this perspective. Well, I don't think I'll have time, but let me, I just make a remark that we assume that kinetic energy flux is constant in MSD. That's not true. Kinetic energy flux should decrease with K, and we find some evidence that should decrease with K in MSD. And walls also, I'm not thinking of walls, but as soon as we have convection, then walls matter. Walls matter. And wall matters in some other ways. Let me, since I'm talking in a very general way, dissipation rate U cube by L by Kolmogorov theory, but for convection, this is not U cube by L. Okay, so this is a doubt. In fact, walls make corrections to this. So that's another violation of any universal theory. I mean, as soon as you bring in wall, it doesn't work anymore. This is not true. Now, buoyancy-driven flows, these are two different scenarios. In fact, this is the picture I think made by Abhishek, not thinking he made this. So in thermal convection, we heat at the bottom and cool from the top, right? So density is strong, large here, and density is small here. But stably stratified flows is other way around. Density, I mean, it's gravity is quite well, gravity strong. So here rho is more and rho is less. Okay, so density is in reversed. As a result, this is unstable. RBC and related flows are unstable. If dense fluid is sitting on top, is unstable, of course. If the dense fluid is sitting at the bottom, is stable. Okay, and as a result, the two phenomenologies are very, very different. Okay, and that is one thing we did some time back. So this is the equation. So this is the forcing. Okay, this is a forcing, which is my F, buoyant forcing, Fu. Okay, now this is active at all scales because temperature is active at all scales. Of course, this equation for theta, temperature fluctuation or density fluctuation. You can think of, we write in terms of temperature only, but you can also write in terms of density. So I will not delve into this equation, but we can construct a very similar formalism for temperature as well. Now, what happens as a result? So there are few non-dimensional quantities. I'm sure everybody knows about this. Prandtl number is nu by kappa. It's density diffusivity, and Rayleigh number is the buoyancy by viscous, and Froude number is gravity times scale by viscous times scale. Okay, there's another quantity called Richardson number, which is approximately nonlinear by is a buoyancy by nonlinear or gravity by nonlinear. Okay, so we are in this talk, we'll basically focus on Richardson order 1. So other scenarios make it non-isotropic. If gravity is too strong, it makes it non-isotropic. But Richardson order 1 isotropic is still okay, not too bad. Okay, so this is what I said. Froude number is order 1 or Richardson is order 1, but it's turbulent. So this work, in fact, Abhishek's PhD work. So so there's a famous theory, Bolgiano-Ubakov theory. So there are two people, Bolgiano and Ubakov, and they constructed theory for stably stratified turbulence. Now here, I will not, my objective is not to discuss this field, which is very vast, but objective here is that here it's a stable flow. So kinetic energy is always going into potential. If you shake the fluid and let it be, don't force it, then it will quietly become a quiet flow. Okay, So the kinetic energy will be converted to potential energy. And finally, the flow will just become very quiet. So, and of course, both kinetic and potential will get into the heat or dissipation. Okay. So there is a conversion of kinetic to potential. As a result, this this is energy transfer from U to density is positive. Okay, so that Fu term, Fuk, if you recall, d pi by dk is Fuk. Okay, so this is force dot u. So that's this quantity is negative for stably-stratified flows, and as a result, now my writing has unfortunately blocked it. So as a result, it turns out the flux is, in fact, let me write it here. I have to write it here because there's something coming below that. Pi uk is k minus 4/5. So kinetic energy is indeed, according to phenomenology, is decreasing with k. Okay, and spectrum, because kinetic energy is decreasing with k, is steeper than 5/3, is minus 11/5. Okay, because there's less energy down at larger wave numbers, because it has been depleted. There is a okay, so I make an analogy which is slightly humorous. So corruption at large scale, corruption, at large scale or intermediate scale corruptions. So this energy supply from federal government, okay, let's assume that the money supply, and it goes down, 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 down. If there's no corruption, then finally all the money supplied at large scale will go down to people. No, so that is one. However, if there's corruption taken by people at the politician level or at big level, then money reaching people will be lower. Okay, so this scenario is corruption scenario where we are taking away some energy or money from the system. Okay, other scenario is philanthropy. So if you have some more money being pumped in, along with the federal government, there's some other people are supplying money to the system, then poor people or average people will get more money at the bottom. Okay, so these are, in fact, I wrote one small article relating finance to flux, but which has no takers among economists. But anyway, that's the model. Of course, very simplistic model. Anyway, but it's for fun. Now, so here, so there's another thing which I will not discuss it, but this part is interesting part, that flux is decreasing, and it's consistent with the variable energy flux. Now, it was Abhishek who simulated this flow, but resolution was only 512 cube. As a result, we could not really get a very clear proof that Bolzano-Bokov theory is correct or not. There were past work by Kimura and later on by Anik Puquet and her group. But this one is basically 11/5 is this for top one is better. 11/5 is doing better. Okay, we normalize it. No standard. I multiply energy spectrum by 11/5 or 5/3. Which one is better? Okay, so its resolution is not great. But okay, nobody had done in the past, so this paper did get through in PRE. And the flux, this is the flux which is decreasing with k. And if you multiply with 4/5, not great, but it's okay. I mean, this is a 4/5 is we are verifying it, and minus fk is positive. So fk, which in fact the notation was different. So this fuk is energy transfer is negative. Okay, so it's consistent with stably stratified variable energy flux formalism. Now, what happens for RBC? Now, in fact, there was a lot of debate. In fact, among the turbulence thermal convection people, some people say it is Bolzano-Bokov, some people say it is Kolmogorov. Kolmogorov-Bokov. Okay, so this is 11/5, and this 5/3. Now, so which one is it? I mean, okay, I don't see you guys, so I can't really ask this question and kind of get you to think about it on the spot. But it is clear to me, okay? In fact, it's clear to us, Abhishek's PhD work. So here, what is the sign of this energy flux? Or energy injection rate? Is it positive or negative? So Bolzano-Volkow theory, it is negative, okay, because the energy transfer from kinetic to potential. But in thermal convection, it should be positive. In fact, this occurred to me when I was teaching a class, in fact, this turbulence class. So, in fact, that time it just struck, look, Bolzano-Volkow cannot work because if I keep this fluid at rest and start heating, the kinetic energy grows, picks up. So FUK for thermal convection is positive. Okay? It cannot be negative because the thermal plumes are feeding energy to kinetic. Okay? So Bolzano-Volkow is ruled out completely. Okay? There's no doubt. I mean, I think that those papers should be rejected, according to me. I mean, if you say Bolzano-Volkow, it is energetically impossible. In fact, Bolzano-Volkow never said that it works for thermal convection. And they were focused on stably-stratified turbulence. In fact, they were very influential scientists, Procaccia, Victor Lava, Falconer. They had argued for Bolzano-Volkow. Okay, it was field theory. I think they missed the sign. Okay, now I have not dug into the full details of the paper, but you can see that they did miss that sign. FUK, they assumed same thing, negative, but it should be positive. And a lot of closures. No, closures are, you make a model and you if you make it negative for energy injection, it's all wrong. Okay. Now, so the flux should increase. In fact, Abhishek and me, we were looking for signs that flux should increase. And the spectrum should not be steeper than 5/3, not 11/5, but should be shallower than 5/3. So maybe 1.5 or 1.4. So we started looking for it. But it turned out the spectrum is 5/3. Okay, for a very interesting reason, which we know now. So this is in NJP, New Journal of Physics. So this is 4,000 cube. In fact, Abhishek did this on Shaheen. So I should acknowledge this is done in Shaheen, a collaboration with KAUST, Shaheen 2. And this was the biggest, I think still the biggest in thermal convection. Okay, so 4,000 cube. And we multiply again by 5/3 and 11/5. So this 11/5 and this 5/3. So 5/3 is definitely winning, right? 5/3 is flat. Okay, so this is a clear proof that it is 5/3. It is not shallower. Shallower would have been, it won't be straight line for that. And the fluxes, both the fluxes are constant. Okay, so pi u is constant for this RBC. It is not decreasing like Bolzano. But I also have one point that people don't look at the flux, unfortunately. They all the focus on spectrum or structure function, but not on the flux, but which carries real information. Okay, according to me, of course, spectrum also carries information, but the flux has a real information for the phenomenology. Okay, now why it is 5/3? It is because the FU, this energy injection rate, FUK, is pretty much, well, it is not large scale only, but it is 5/3. Okay, it turns out this was Prandtl number 1. I must say that this Prandtl number 1. If Prandtl number is changed, then again theory deviates. It is not 5/3 anymore. But for Prandtl number 1, the energy injection rate is decreasing relatively fast. Okay, it is not, well, it is not large scale like Kolmogorov large scale. Kolmogorov theory says that okay, it is like that. But here, okay, it is dropping very fast. That's what I can say. It is not zero for intermediate range, but it's dropping pretty fast. Okay, so that is why it is 5/3. This spectrum is like Kolmogorov theory. Okay, there are some changes. So if you look at the inertia range flux, it is not equal to the dissipation rate. Okay, in Kolmogorov theory, we find that the inertia range flux equal to dissipation rate, but it is a dissipation rate, but it is not so for convection because it is forcing at all scales. Okay, there are some subtle changes, but on the whole, the phenomenology is approximately similar. Okay, so I'm sorry, yeah. So we can change the Prandtl number, and we get basically. So these are different Prandtl numbers. So this is work by Saswat, a PhD student who just graduated, and He basically painstakingly did for Prandtl number 100 downward to 0.02, and Prandtl number 0.02 shows 5/3. Now this cumulative spectrum, so it is not 5/3, it's 0.68. Okay, so you have to add one to that. It's cumulative, no, it is summed. So you have to add, so subtract one, so it's 1.68. But if you go to 100, Prandtl number 100 is dropping steeply. So it is like 3.6362. Okay, and Prandtl number 100 is dissipative. It's in fact more like viscous flow. So you expect that. So you can again, this indicates that world is very rich, and there's no one fit for describing even convection. Convection has no single spectrum. It has pretty much, it depends strongly on Prandtl number. Now, one more interesting point we observed, which was very puzzling, but we know now why it is so. The temperature fluctuation has dual spectrum. So there's a -2 spectrum, there's K -2, and this part is not 5/3, anything like that. The bottom part. So we know -2. Why it is so? Because the temperature basically boundary layer drops suddenly, then the constant in the bulk and drops suddenly. And if I look at theta, which is a fluctuation, so T, this one, okay. So this is the total temperature. Okay, this is total temperature. Okay. Now we have to subtract the T conduction part. Okay, and T conduction part has a linear profile. Okay. Now I don't want to belabor on it, but here again walls matter. That's what I would like to say. Dual spectrum was very, very funny, and we thought there's something wrong with the code, but since there's a wall, we have this conduction profile, and that matters. The boundary layer and the theta has dual spectrum. In fact, it has been seen by other authors too. Not highlighted enough, but we see that. And I expect the channel flow also to show some kind of dual spectrum. Okay. Okay, we're not, I mean, okay, this has not been very checked again, but that's what we expect. Now, quickly on a rotating flow. Now, rotating flow, this was again a surprise for us, and this field, I mean, there are lots of work, but we went to pretty fast rotation. Okay, our Rossby was 10⁻³ or so. Okay? Very fast rotation. So this was done by Manohar. So here there's another force, Coriolis force. If you there's a force. Okay. Now this will have some consequence on the spectrum and the flux. And there was something funny for very fast rotation. So for very fast rotation, there are basically columns. They are not Taylor columns. Taylor column is for lower roll end numbers. Okay, so these are not kind of steady flow. So there's some kind of inverse cascade has happened. Okay, so that led to this stuff. Okay, similar columns, but in the referee himself said or herself that these are not Taylor columns. So they're basically arises out of nonlinear effects, which is ignored in Taylor's derivation. Now, so these are at different times. Now it is blocked in my computer. So this is 149 eddy turnover time. Okay, and this is around 100, and this is around I don't see that around 50. Okay, so these are ran for a very long time, and we basically get one vortex. This periodic boundary condition. So this is same as well. They combine and okay. Now, if you look at the flux, you find that the plot is slightly small, tiny. So these are at different times. Huh? So this is T equal to 4. This is T equal to 4, and there is some inverse cascade. There is a negative flux, kinetic energy flux. Huh? But when you go to 49, 148, these are essentially pretty tiny, 10⁻². Okay, that this one 10⁻². Now, so I can't really construct a theory. I mean, we have been focusing on flux. So, well, what do I do with flux is very tiny. Then let's look at 2D turbulence. Well, they're tall these columns. So we make a cut and then just look at the 2D flow. And then let's look at the entropy flux. So this was just searching around for some clues. And the entropy, this entropy, omega, this is entropy, okay, omega squared. And that entropy flux is somewhat constant for small range of wave numbers. So these are like this is okay, 512 cube. Some runs with 1000 cube. So the one run 1000 cube, but 512 cube we get small region of constant flux, and then it decreases. Okay. Now, since the range of constant flux is tiny, so we wanted to model the whole thing, this part. And it turned out this is a nice model, and the model is that we go back to again variable energy flux, but now not for the kinetic energy, but for the entropy. Okay. Now there's no forcing, right? In this, there's no, well, there's forcing Coriolis force, but that doesn't really inject energy. The forcing dot u is 0. Okay, omega cross u dot u is 0. So this is changed only by the dissipation. By the way, dissipation I've actually all scale. Even for 3D hydro, there is a dissipation, but dissipation basically gets dominant for slightly larger wave numbers. But here it starts dominating at small wave number itself. Here. And now let's solve this. Of course, unfortunately, this equation cannot be closed because there are two unknowns and one equation. But we applied this pause model where we can write down pi omega by EU epsilon omega is the dimensional analysis. It depends only on k and flux, not on nu. Okay, so that turns out to be k minus 1. Okay, now as a result, again, sorry, this was it has been blocked again. So you can see that the flux is dropping as exponential, and exponential minus k squared. Okay, so that is a drop of flux, and spectrum also drops as it is k minus 1. This Kirkland theory, in fact, but Kirkland theory does not talk about the dissipation range, and dissipation range we can, of course, if you believe in pause model, or well, we don't know, we're not verified the pause model in real ways, but if you believe pause model, then we get k minus 2 exponential k minus k squared. Sorry, exponential minus k squared for that dissipative part. Okay, and it turned out it was a good fit for this. So for very fast rotating turbulence, we had these columns, and the basically turbulence is quiet and is more like laminar. Okay, so of course nonlinear term is there, but it is weak, and so we get these are fits for this. So this left part is entropy spectrum normalized with k, so I multiplied by k, and the right side is all the entropy fluxes, and we fit with this, so that dashed lines are fits. And so here also the energy flux, variable energy flux, gives us interesting ways to model these flows. Okay. Now I'm almost towards the end, so we can apply this to many systems. So just to list some of them: quasi-static MSD, equine friction, stiff. So we've done some of it ourselves, thermal convection, and some are of course done by others. Unstably stratified flows. This unstable, so it's like RBC. MSD, recently we've been trying to do it. Polymer, shear turbulence, Euler. Okay, so we can use this formalism to understand what happens to the flux. Qualitatively, what happens to the energy spectrum. Some of it is very rich. There is no in one theory. I mean, you can't say spectrum will be k minus alpha. Okay, no, it keeps differing for different parameters. Now, I just want to say that for MSD, which is of interest to I think many people in the group of Coventry. So kinetic energy is lost to magnetic energy in dynamo, no? U to B. So we expect the flux of U, the pi U, to decrease with K. I expect it. It may be weak decrease, but it could decrease. Often we plot the y-axis as a log scale, but we should not plot in log scale. If you plot in linear scale, you may expect to see some decrease. But we have, well, I mean, this is something to be explored. We're trying to do it. Some results, but not very. We need high resolution simulations. Okay, so just to conclude, I believe there's no universal theory of turbulence. In fact, we can't even look for one because it's too rich. And also it's a macroscopic. Of course, like gravity is rich too. Quantum field is, quantum mechanics is also rich, but it's a microscopic field, so well, Newton's laws works at all scales, so I can't say that, but there are systems which work at small scales, and there may be some universal theory, but as soon as we have multi-scale stuff, then maybe not. I mean, that's what. So there's some generic tools, like flux is one such tool. So there could be a more. Like entropy could be thing, but entropy is, in terms of temperature, is not a very good thing, because we don't have temperature well defined for many of dynamical systems. Okay, now, so I've been saying that macro world has a disparate, very different kind of phenomena, and we need multiple theories, not one theory. Okay, so I try to argue in this small paper that we need many laws, not a single law. So I'm going against this framework of one theory, one equation, one Lagrangian. I don't believe that is the case. In fact, this is a motivation of this work from that. Okay, thank you for your attention.
Thank you, Mahendra. Question?
Yeah, Abhishek, I can't hear you well.
Thank you, Mahendra. Questions from audience here, or whoever, or you can, someone who is online can write in the chat box, or just say by taking the mic on.
Yeah. I can ask one at least.
Yeah.
I was wondering if you push the reasoning a little bit further. I don't know if you can hear me here. Where's the microphone?
Microphone is here.
Make it close, otherwise. Can you hear me, Mike?
Hi, Alman. Yeah, I hear you. Yes.
Yeah, I was wondering if you push the reasoning a little bit further. So you let's particularly the case with negative flux. So you start with a certain amount of energy at large scale, and it goes down. And flux, then energy is being pumped up. But it does mean probably that also the small scales are going to change as a result of that, because you deplete the amount of energy they get from the start at a different rate. So that means the Kolmogorov small scales will also depend on that. Did you look at this?
So you're saying the flux is negative?
Yes, you take one of the, typically, well, it would also work with a positive flux, but I think it's more physically easier to understand. So if you start from the Kolmogorov picture, you have a certain amount of energy, and it goes down the cascade.
Right. Okay.
Then you reach a certain level of small scale. Now, if you have a negative flux, you pump energy in the intermediate process, but probably the small scale should move as a result. It should move up, because you deplete the amount of energy before you reach the Kolmogorov scale. Is that right?
Right. Indeed, very good question. Alban, so we try to do 2D convection, thermal convection, 2D. Okay. Now, 2D thermal convection, what is the spectrum? It's in fact very similar idea. So let me see whether it kind of interests you. So let me try to get, let me just try to write something. So in 2D turbulence, we see the flux is negative, right? Flux pi. Now, so if I now apply gravity, okay, and I apply gravity, then what happens? So it turned out we expected the flux to go like that. In fact, because, okay, now I had to worry about the, so if I, so there is way to worry about even for the inverse cascade. So we have a sphere, you see, we have two spheres. And if I supply energy here, energy is going in like that. Can you see my pictures now, pi? Now what should be the pi for the low inner sphere? should be bigger, no? This pi, this will be bigger in magnitude. A will be bigger than B. Correct? Because I'm supplying inside, but flux is negative. So this should be the sign of the, this should, it's a negative, but it should be going down in that direction. So indeed, I think for inverse cascade 2, these arguments can be made. Yes, I mean, so in fact, Kolmogorov may work for 2D or at least boundary layer. Okay, boundary layer, we've been trying to think, look at it like that. So inverse cascade 2, I think is interesting. I mean, we can look at it like that. Did I answer your question, Alban?
Actually, it was general, but that's an example. Yes. Yeah. Thank you.
Yeah, indeed. I mean, of course. So it's an energetics argument. We can go backward, forward, but indeed, yes.
I'm not going to steal the show. So.
Any more questions? Let me see if there is anything in the chat box. No.
Hey, chat, any question in chat? I didn't see that chat. No question.
Okay.
I have another one.
Okay. Yes.
I have another question.
Please,
I don't know if
please, Alban.
you might have seen that it's an old paper by Sven Eckert, 2001 paper in a quasi-static MHD. And what they had done, they had a dot and a grid, and they were measuring turbulence behind a grid in liquid metal with a magnet.
Okay, yes.
And
Yes.
they did something very interesting, is that they tried to see how the slope of the energy spectrum varied with the magnetic field.
Right.
They found, because at the time, I think the paradigm was that, well, yes, the energy turbulence quasi-static gives you K-3. That was the paradigm from the old Alimani paper, and there was an argument for it, but the argument required as the interaction parameter is 1 approximately. So what varied that? So he varied from low interaction parameter to quite high interaction parameter, and he found that the slope varies hugely, in fact. So at low interaction parameter, you get the K-5 because the magnetic field doesn't do very much, and as you increase the parameter, it decreases. The slope decreases significantly to -4, in fact. So there is a point where it gets -3. It gets actually -4, and then it goes up again. So I was wondering whether, with your theory, you could actually try to match those results.
Yes. We have 2 papers, Alban, on this. So this is so in fact, just write down d pi by dk. Okay, as energy coming out, which is this term, right? B naught square or n cos square theta ek, average over theta. Then we basically get n cos square. Well, basically n ek. Okay. Now again, we need to close it, right? Because there's pi and u. So we use Pau's argument. So we've been using Pau very often. For good reason or bad reason, we wanted to close it. So there's a minus sign. So basically, there's a huge depletion for strong interaction parameter of flux. Well, at strong interaction parameter, the flux will be suppressed even larger. So spectrum can be anything. It could be -3, -4, -5. In fact, we also got exponential spectrum. You got d power -k for large interaction. In fact, one of the referees for like Sandeep Reddy, he did that work, and we found that the exponential is a better fit to his experimental work. I know this. We looked at this his experimental work, and exponential was a better fit rather than K-6 or K-5, I think. Okay, K-5. And then we showed we made a model for this as well for interaction parameter beyond 100. The spectrum EK is exponential. So I'll send you that paper. Is there in my ROPP, Reports on Progress in Physics, 2018, I think. I describe this in quite a bit of detail.
Okay. The thing is that in their experiment, when they reach a too high interaction parameter, there's something drastic that happens, is that the turbulence becomes 2D, but quasi 2D because they have walls. And
yes,
dissipation becomes driven by the walls. So that is not in there, I think.
No, but I think the cascade sign is still positive for very strong parameter. So by the way, this idea will work even for anisotropic, very strong anisotropic. Like for rotating turbulence, the flow is very, very anisotropic, right? Still, we can apply this idea of the variable flux.
Yes, but the point is that when you reach that regime, the dissipation mechanism changes completely. Because
so dissipation is indeed, it's a Joule dissipation is dominant, not the viscous dissipation.
No, but in fact, that's not what happened in quasi 2D regime, because there is practically no dissipation in the bulk. So all the dissipation takes place in boundary layers when you reach a very strong dimension. That is not here. But I think
okay, yeah, boundary layer we are not covering in this work at all. So, yeah, that part I agree with that. Yes, but as long as we are talking about the bulk, flux will be okay.
Yeah. But after you get standard 2D turbulence plus an extra dissipation bit. Yeah.
Yes, yes.
So yeah, that's interesting. Yeah, I'll take a look at that paper. Thanks.
Yeah, yeah. Thank you.
If there is no any more questions, then